goal is that of simulating the management of a reservoir. We keep the stream flow time series that we have generated in the previous homework, and you force the reservoir and you play with the opening degrees of the spillways, in the essence, and you generate a transformed time series of discharges downstream of the dam. In particular, the focus of the homework is about the interplay between hydropower production and flood control. So, simulation of management operations of the Corvo reservoir for hydropower production and flood control under different scenarios. In particular, we have the scenarios summarized here. The first one is about only hydropower production, so we don't care about maximum discharge downstream. In the second case, you have at the same time hydropower production and flood control downstream, which means that you care about the maximum discharge downstream of the dam. And there are different options with maximum level in the pool to allocate the upper portion of the reservoir to mitigate floods. And this can be done with a permanent maximum level or with a temporary maximum level, with and without meteorological forecasting, meaning that you have some time prior to the event to decrease the stage in the pool and meet the maximum level imposed to mitigate floods downstream. So that's what we are talking about. This is done to understand the interplay between management of the reservoir, natural stream flows upstream, and downstream regimes. Okay, this is the principle according to which the processes we deal with operate. So the reservoir balance, variability of the storage in the reservoir dV over dt, is equal to Q in minus Q out. So all the input fluxes minus all the output fluxes. In particular, we have a number of Q in and a number of Q out. As usual, we also have in the mass balance the evaporation from the lake, directly from the lake, and the precipitation over the lake in rainy days. In this case, we have a numerical model, so we also take into account direct fluxes on the lake, but we almost know that a priori these two terms, E and P, are smaller than the others. Okay, so the list of the terms is represented here. The unique input beside precipitation on the lake is the stream flow entering the reservoir, Q in. And this is what you get from the file stream flow in that you have produced with the previous homework. P is the precipitation on the lake, as I was saying before. This can be estimated using the file rain downscale that you have generated in the first homework. Okay, evaporation from the free surface is assumed to be positive only in days in which we don't have rainfall, because we assume that when there is rainfall, the net radiation is not sufficient to evaporate water from the lake. Q out is a kind of complex term, but because it is made up by many components, in this case, in particular, we have different spillways for different functioning of the reservoirs. So we have a minimum environmental flow spillway, something that is designed to deliver something downstream of the dam, QMEF. We have a spillway specifically designed for hydropower production, so taking the water from the lake and bringing that water to the power plant, which is QHS. We have some flow released downstream through the intermediate spillway of the lake, in the middle of the dam, let's say. And then we have two crest spillways on the top of the dam, that they act as overflow somehow. Okay? So we have different spillways operating at the same time in parallel, releasing water or removing water from the reservoir. Okay? Minimum environmental flow, hydropower production, intermediate spillway, crest spillway. Okay. Now, evaporation as I was saying before, evaporation is only active when precipitation is 0, and you can calculate this constant, this evaporation rate, using the Penman approach, more or less in the same way as you did for the computation of evapotranspiration in the second homework, with the only differences that I have been already discussing a few classes ago. Okay, this data E0, the evaporation rate in not raining days, in centimeter by day, has to be placed in the input file, climate and basin. Of course, okay, this is a code, so we have an executable file as usual, then we have a folder input with a sequence of input files, and then we have a folder output, and when you run the code, all the output files are produced in the output folder, and you have to set up all the files in the input folder in a proper way so as to run the code. Okay, so one of these, now I will be explaining you quite quickly all the files that you have to set in the input, and in the input you have to give all the information needed, telling the code how big is the reservoir, how big are the spillways, how big is the catchment, how is the evaporation rate in this case, and so on. Okay, so from now on, 20 minutes or so, I will explain you all the information that you have to give to the code to make it function. Okay, so the first information I'm discussing is the evaporation rate. It is placed in the second line of the climate and basin file, and it is something that you have to calculate offline with the Penman approach. And the second information in this file is the catchment area. That is, I think it's already set in the example input files that you have in Moodle. Okay, this is about the property of the climate and the property of the basin forcing the reservoir. Okay, now spillways. We start with the minimum environmental spillway. Okay, we know the formula of the minimum environmental spillway because it is exactly the same formula of generic spillway. So we have a discharge coefficient, we have the area of the spillway, we have an opening degree, theta, and then we have the square root of 2 times the gravity acceleration times the head over the spillway, that is z, the elevation in the pool of the lake, minus the elevation of the spillway itself, z m e f. Okay, so the first 3 guys, discharge coefficient, area, and elevation, about the geometry of the spillway, you have to set these numbers in a file that is termed reservoir. And in the file reservoir, you place all the information about the geometry of the system. The opening degree of the spillway, instead, you have to set it in a different file that is called hydroelectric, containing the opening degrees of all the spillways. Okay, this is what I'm talking about. You see the 2 files, reservoir and hydroelectric. In particular, you see in the upper plot, in the upper screenshot, you see the file reservoir. You see in the second line, you have the area of the spillway, the elevation of the spillway, and the discharge coefficient of the spillway. A, Z, and C. In the hydroelectric file, instead, you have a number of information, mostly related to the hydroelectric production and the opening degrees of the spillways. I will explain this later. And as you can see in the second line, again, you have the opening degree of the spillway for the minimum environmental flow. In this case, 0.2. Okay, you have to set it somehow. Clearly, if you set 0 here, you don't have minimum environmental flow. The true minimum environmental flow released through this spillway depends on the stage, clearly, right? According to this equation. So clearly, the idea is to set it somehow, a relatively small value, so it has to get some minimum flow discharge downstream. And the idea is to verify that the minimum flow discharge is actually fulfilled. Okay, clearly, the larger this number, the more water you are releasing downstream through that spillway. If you release water through that spillway, you cannot process that water for hydropower production. Okay? So, in some sense, there is a trade-off. Okay. Let's move on. What about C? Okay, C is something that depends on the geometry of the spillway, as the hydraulic laws prescribe. In particular, in this case, how do you calculate the discharge coefficient for the minimum environmental flow spillway and for all the other spillways? You have in a document, a Word document that is provided to you, you have information about the discharge released through different spillways depending on the stage in the pool. So you have Z, height of the water in the pool, and you have discharge. So essentially you know the stage Y in this relationship, you know the area of the spillway, you know the discharge, and so you know the velocity, and so you create a plot where you have the velocity, discharge divided by the area on the y-axis, and you have the square root of 2 times the gravity acceleration times z minus z and if, so the head over the spillway, and you plot the experimental points that I give you in the document, and then you calculate the slope on the of the interpolating lines, and you derive the discharge coefficient. Okay, this way. I don't want to give you just the geometry and let you calculate that from the geometry. I just got the project, and according to the designers, there is this relationship between stage and discharge. So based on that, you back calculate the discharge coefficient. Okay. You do this for the minimum environmental flow of this spillway. In this case, clearly you have 4 tables: one for the minimum environmental flow spillway, one for the intermediate spillway, for the crest spillway, and so on. Okay. So the same operation will be done also for the other spillways. Okay. Second important output term from the reservoir is the stream flow directed, diverted from the lake for hydropower production. The formula is exactly the same as before. We have discharge coefficient, area, opening degree, and then we have the square root of the 2 times the gravity acceleration times the head over the spillway. In this case, clearly the level of the spillway is different than the minimum environmental flow spillway. So for all the spillways, beside tables of this type, you also have, I think it's the information here. You see, 230 meters. So you have also the height of the spillway for the different spillways. Okay. So again, discharge coefficient, area, and height in the file reservoir.dat. In the spillway opening degree is something that you have to manipulate because you have to run the model with different opening degrees for the hydroelectric production to see what happens. So this is something that you have to change to see the effect on the energy generated, the revenues from the selling of the energy, and the flow regime downstream. And this has to be changed in the input file hydroelectric, the same as before. Again, I provide you with screenshots. You see the reservoir file and the hydroelectric file. Again, in line 3, in this case, area, height, and discharge coefficient of the spillway for hydropower production. And in line 3 of the hydroelectric file, you have the weekend and the weekdays opening of the spillway for hydropower production. As you know, the price of the energy is different during weekends and weekdays, so this is why we have 2 different opening degrees during the weekends and during the weekdays. So you can differentiate the energy production during the weekends and the energy production during the weekdays. Okay. So these 2 have to be changed, trying different combinations to see what happens and to see what is the best solution from the viewpoint of the water manager. So from the viewpoint of the energy produced and the revenues from the energy selling. Okay. Intermediate spillway. Same rule, same information. Also in this case you have a document telling you something about the height, the area, and data to calculate the discharge coefficient, and you have to put this in the input file reservoir. In terms of the opening degree of the intermediate spillway, this is something that is not is an information that you don't have to give to the code, because automatically the intermediate spillway is closed almost in all the times. This is because physically we know that the intermediate spillway of the core reservoir is typically closed almost all the times. But to eliminate, to help reducing the stage in the pool to meet a maximum level bond to mitigate floods, the code automatically changes the opening degree of the spillway, of the intermediate spillway, during floods from 0 to 0.2. This is functional to reduce the stage in the pool and meet as quick as possible the maximum level that is prescribed to let the upper portion of the reservoir available to store water and mitigate floods. Okay? So this is something that you don't have to change. It is automatically set by the code itself. Okay? Okay, and again you see that in the reservoir file, in the third line, you have area, height, and discharge coefficient also for the intermediate spillway. And for the intermediate spillway, this information is taken from a table where you have stage and discharge exactly as this guy here. Okay? So here you find the area, you find the height, and you calculate with a plot of this type the discharge coefficient. Okay, when the intermediate spillway is activated, and some stream flow leaves the reservoir through the intermediate spillway, as a consequence, a message is reported in the output file report. So you see, intermediate spillway has been activated at the time step, and so you know that this happened if you want to check it. Okay? This file report is nothing more than a sequence of information related to what is going on. Typically, you don't have to check this report, but I mean, there are summary information about the type of simulation that you're doing. If you don't remember what you said to the code, here you can find a summary of the simulation that is going on and some other additional information about what happened during the simulation. Okay? This is an output, okay? This is an output of the code itself. So this is not an input file. It's something that the code produces to just keep track of what is going on. It is in this slide only because I'm telling you if the intermediate spillway is typically closed. So the discharge to that is typically 0. If this is not the case, you can check it in the report file that is one output of the code, because you get a message of this type. If you don't, this means that during all the simulation, the discharge leading through the intermediate spillway is 0. Okay, crest spillways. Okay, in the core reservoir we have 2 crest spillways operating at the same time, but with different heights and different shapes. Actually, to tell you the truth, one of the 2 is regulated. But for the sake of simplicity, in your homework, we assume that both the crest spillways are unregulated. Otherwise, you would have to play with another degree of freedom of the system, and the homework is already kind of complicated. Okay? So we have two different reservoirs, two different crack spillways in parallel. The first